Hello, I'm Leonardo, and today I will be talking about the paper Deep Learning Alternatives of the Kolmogorov Superposition Theorem, which was accepted to ICLR 2025 as a spotlight paper. In this video, I will go over the Kolmogorov Superposition Theorem and some of its important variants. Then, I will introduce ActNet, an accurate and scalable alternative to Kolmogorov-Arnold networks. I will then conclude by going over some experiments where we observe ActNet consistently outperforming alternative methods. The original version of the Kolmogorov superposition theorem was proposed in 1957 to address Hilbert's 13th problem. This theorem provides a way to exactly represent an arbitrarily complex continuous functions in d dimension using only univariate functions. It also does so using a finite and fixed number of functions. There have been many attempts over the past half century at adapting Kolmogorov's theorem for computational tasks, but most recently, Kolmogorov-Arnold networks, also known as KANs, appeared as an attractive approach to integrating the theorem with modern deep learning. However, more recent papers indicate mixed results when employing this architecture, motivating the need for more research in the field. In particular, several variants of Kolmogorov's formula have been developed throughout the years, each with different flavors and assumptions. Although Kant's take inspiration from the original version of the theorem, an important question to ask is which is the right formulation to be used in deep learning algorithms. In particular, the original version is one of the very few where the number of inner functions implied grow quadratically with the input dimension as opposed to linearly. Based on our research, we believe Lashkovich's version presents a promising direction. This version retains some important features of the original KST, but provides better generalization and uses a computationally simpler formula. Its domain is valid all of Rd, as opposed to just the unit cube, and it also provides a flexible width representation and a number of unknown functions that scales linearly instead of quadratically. Using this formula, we approximate the unknown univariate functions as linear combinations of basis functions and learn the relevant constants via gradient-based methods like atom. We also generalize the structure of this formula to allow more compositions, making the final architecture deeper and more expressive. Using some linear algebra, we isolate a key block from the theorem's formula, enabling parallel computation on GPUs. This approach results in a unit we call the act layer. The input to an act layer is processed in parallel by m trainable nonlinear functions acting as tunable activations. Each transform vector is then dotted with a learnable vector to yield the ith entry of the ith layer output. An optional bias parameter can also be added at the end of this block. This layer can be equivalently seen in two ways, as an approximation of the formula implied by Lashkovich's version of the KST, or inspired by multi-head attention from the transformer literature as a multi-head MLP layer where each head has output dimension 1 and a tunable activation. By composing many of these layers together, we then create an ActNet. This architecture also uses linear projections at the beginning and end of the network, which boosts performance in some tasks. ActNet boasts universal approximation properties, which are derived from Lashkovich's version of the KST. By designing a suitable basis for the inner functions, we ensure stable intermediate activations, allowing us to train deeper architectures. We prove that activations will have mean 0 and variance 1 at initialization, and using the central limit theorem, showed that their distribution approaches the standard Gaussian as the network size increases. ActNet is considerably faster than Kant's, running at slower but comparable speeds to an MLP of comparable size. We conduct experiments for learning solutions to partial differential equations using the PINS framework, where solutions is determined using derivative information in a data-free manner. Although we see ActNet as a general-purpose architecture, we believe it is particularly suited for applications requiring derivative information, as its higher-order derivatives do not vanish, unlike those of most ReLU-based architectures. Our experiments show that ActNet performs remarkably well when compared to architectures such as SCUNs, Sirens, and plain MLPs. We train over 7,000 independent networks for ablation studies as our best attempt to provide a fair and thorough comparison. We see the largest gap between architectures for complex problems showcasing high frequency content, indicating that ActNet is less susceptible to spectral bias. ActNet is also competitive against state-of-the-art architectures for pins, such as SpiroNets and the modified MLP from JackSpy. In a chaotic system, we also observe ActNet displaying more stable rollouts than alternative methods. Thank you very much for your attention, and feel free to contact me with any questions. I'm listing here some useful references if you'd like to learn more about our paper.